Now what we will do is we will integrate this equation twice because we have square, so we will integrate this equation twice. Now del T would be equal to minus qx upon k plus c1. C1 will be the constant which will be introduced, okay, which will be introduced when we will integrate this equation once. Now once again we will integrate this equation. 2 is equals to T is equals to minus qx square upon 2k plus c1x plus c2. This will be the equation after integrating it 2 times. Please note this equation. You can directly remember this equation in order to solve any problem in case of slabs. That is T equals minus qx square upon 2k plus c1x plus c2. c1 and c2 are the constants. We have c1 and c2 are constants. Okay, C1 and okay, so C1 and C2 are constants, and please remember this equation. This is very important equation because in GATE there was one question asked which was directly from this equation. So if you have remembered this equation, you can very easily answer that question. We'll be doing all the numericals at the end of the chapter. Okay, now if we need to find out what is the location of maximum temperature, we need to find out what is the location of the maximum temperature. Now in order to get maxima and minima for T max, what we will do, we will have del T upon del X equals to 0. We will have del T upon del X equals to 0. Now if we talk about the boundary conditions, X equals to minus L, T equals to T wall. At X equals to 0, T equals to T maximum. The maximum temperature will be in the middle and the profile of the temperature will be like this. Here we will have the maximum temperature and the temperature profile will be like this. Okay, and at X equals to L, T equals to T wall. So by using these boundary conditions, the constants C1 and C2 can be easily evaluated. Okay, and please remember one thing, that T minus T naught upon TW minus T naught equals to X upon L whole square. This is actually the dimensionless format. Of the temperature distribution. This is the dimensionless format of the temperature distribution. T is any general temperature, T naught is the maximum temperature, TW is the temperature of the wall, that is either of the extreme right or of the extreme left. Okay, and X upon L. X is the coordinate, L is the length of the slab. Okay, so from this equation, this equation, if I wish to write del T upon del X, the value of del T upon del X, that is del T upon del X, it would be minus Qx upon K plus C1. Minus Qx upon K plus C1. This will be the del T upon del X. Now in order to have max temperature, this del T upon del X is equals to 0. This del T upon del X is equals to 0. Now from here we will find out what is the value of X corresponding to which del T upon del X is 0. So the value of X which is given here, or that will be obtained here, it will be the value of this location at which the temperature becomes maximum in the profile. Okay, now we will discuss about the heat generation in case of a rod or a cylinder. Okay, now you need not to remember that equation. I am simply writing it down for the sake of your convenience. That is del square T upon del R square plus 1 upon R del T upon del R plus Q upon K equals to 0. This is the general heat conduction equation for cylinder or a rod, definitely for a rod or a cylinder, and heat will be conducted radially outwards. Okay, now we again integrate this equation 2 times. On integrating it once, we will get del T over del R equals to minus QR upon 2K plus C1 upon R. In order to find out the value of R at which the temperature is maximum, what we will do? We will simply do del T over del R equals to 0. The value of R that will be obtained here will be the value corresponding to which the temperature will be maximum. Now, again if we integrate this, we will get T is equals to minus QR square upon 4K plus C1 log R plus C2. This will be the final equation after integrating it 2 times. Now, if we look at the previous equation, if we look at this equation that we have obtained here, this equation T is equal to minus qx square upon 2k plus c1x plus c2. A very similar equation will be obtained here also, that T is equals to minus qr square upon 4k plus c1 log r plus c2. Okay, so this equation should be remembered directly. So as to solve the numericals. Now, if we draw the temperature profile in case of a cylinder, then the temperature profile will be like this, and this will be T0 or T maximum. It will occur at a distance. This is R. Okay, this is T0. T0 is the maximum temperature. Okay, now in this case, if we wish to write down the dimensionless temperature profile, it would be T minus T0 upon T wall minus T0 is equals to small r upon capital R whole square. Please remember this dimensionless format. This is called as the dimensionless format. Okay, so this was all about the heat generation in case of slabs and in case of cylinders. Okay, in case of slabs and in case of cylinders. Now we will discuss one very important topic, that is fins. Now, fins are generally the extended surfaces. Okay, if we talk about fins, then fins are the extended surfaces, or they are the projections which are protruding from a hot body. They are generally protruding from a hot body. They are protruding from the hot body into the ambient atmosphere, so as to increase the heat transfer rate, by increasing the area. Actually, they increase the effective area, because of which the heat transfer rate is increased, and the heat transfer rate can be increased by means of these fins, since they have large area. So fins are mainly used to increase the heat transfer rate. They are used in case of they are used in cars and bikes and all. Fins are generally used there. Okay, now I have told you that fins are generally used with respect to the ambient, such that the ambient has only air. The ambient surrounding must be air. It should not be water or any liquid, because then the use of fins would not be that effective. We will discuss why we are not using fins with liquids as the ambient atmosphere in the upcoming lectures. Okay, so it should be generally air. Now we will have the analysis of a rectangular fin. Okay, now we will analyze this rectangular fin such that the area, this is known as the profile area. It is A, Z is the width and T is the thickness of the fin. So perimeter would be, the perimeter of the fin would be 2 times Z plus T, and A is actually known as the base area or profile area. A is known as the base area or the profile area. Now let us quickly write down the objectives and the assumptions. Objectives. What is the objective for studying with? That is to get the temperature distribution. We need to get the temperature distribution First is temperature distribution, second is heat transfer rate, okay, and assumption would be what? Assumption would be first steady state, and second is the very common assumption, that is one dimensional heat flow. Okay, now I'm not deriving all those equations because those equations are not going to be asked in the form of derivation, but you need to remember the direct equation. Now if we discuss about the slope of heat transfer line, it is represented by small m. It is equals to under root pH upon Ka. It is equals to under root pH upon Ka. P is the perimeter, H is the convection heat transfer coefficient of the ambient, K is the thermal conductivity of this fin, A is the base area or the profile area. Okay, then m square would be pH upon Ka. Okay, so the standard format for the equation is d square theta upon dx square minus m square theta equals to 0. This is actually the standard format of second order differential equation. This is the second order differential equation, okay, in case of theta, where m is the slope of the heat transfer. Now the temperature of the surrounding, let it be T infinite, and the temperature of the wall, let it be T0. The temperature of the ambient is T infinite and the temperature of the wall is T0. Now if I wish to write down the temperature distribution, I am writing it directly. T minus T infinity upon T naught minus T infinity equals e to the power of minus mx. This will be the temperature distribution for the rectangular fin, where T naught is the temperature of the base or the root, T infinity is the temperature of the ambient, e to the power of mx, and Q fin, that means heat conduction through the fin, would be equal to under root pH Ka T naught minus T infinity. pH Ka T naught minus T infinity. This is the heat conduction equation in case of the fin. Okay, T naught is the temperature of the base or the root, T infinity is the temperature of the ambient surrounding, under root pH Ka, perimeter, convectivity transfer coefficient, thermal conductivity, and profile or base area. Now there are different cases under the study of fins, and the first case is when the fin is of infinite length. This is generally not possible. Because we cannot have an infinite length fin. But let us say that the fin is of infinite length. Okay, fin is of infinite length. So the formula that we have written by mistake in the upward section, actually this is the phenomena for Q fin infinite is equals to under root pH Ka T naught minus T infinity, under root pH Ka T naught minus T infinity. This is the case of heat transfer in case of fin of infinite length. This was the case 1. Now we discuss about the case 2, that is fin of finite length and insulated tip, such that, let us say, the tip of the fin is insulated. Say this is the tip and this is the insulated tip. Then Q conduction tip is equals to 0 and Q convection through the tip is also equals to 0. Now you must be thinking from where we are getting this Q conduction and Q convection. Then let me tell you. If this is the wall, then from the wall to the fin we will have Q conduction, and from the fin to the ambient we will have Q convection. Okay, please note that this is the most important case, and if none of the assumptions or any data has been given, then we will assume that the fin is of finite length and it is insulated at the tip, and we will apply the formulas regarding to this case. That is, fin is of finite length and insulated at the tip, then Q conduction equals to 0, Q convection equals to 0. Now if I wish to write down the temperature distribution equation, it will be T minus T infinity upon T naught minus T infinity equals to cos H M L minus X upon cos H M L. Here we are having the hyperbolic function of the cosine. L is the length, X is at any coordinate. Okay, T minus T infinity upon T naught minus T infinity. So this is the temperature distribution equation in case of fin, which is having finite length but it is insulated at the tip. If I wish to write down the Q through this fin for case 2, it will be under root pH Ka T naught minus T infinity tan H M L. This will be the heat transfer equation in case of case 2 fin, that is Q is equals to under root pH Ka T naught minus T infinity tan H ml. Here we are having a hyperbolic function of the tan, where value of m, that is value of m is equals to under root pH Ka. The value of m is equals to under root pH Ka. And I am going to write a very important note point, that if no case is mentioned, then we assume it to be case 2. However, for practical purposes, we are never going to insulate the tip of the fin. Rather than we neglect the convection heat loss from the tip as explained below. We are not going to insulate the tip, but for our assumption, we will assume that Q convection through the tip is 0, as the thickness of the fin is very, very less. For example, thickness of the fin is very, very less. This is generally used in case of bikes. Nearly about 3 mm thickness, and radiator. This is used in case of bikes, and in case of radiators of car, the thickness is about 1 mm. So you can imagine how less thickness these two components are having in case of the fins. Now we will discuss about the third and the last case, that is fin is of finite length and it is losing heat at the tip by means of convection. So in the first case we had fin was of infinite length. The second case we had fin is of finite length but it is insulated at the tip. But now we have fin is of finite length and it is losing heat by means of convection. So I am simply writing out the temperature distribution profile. T minus T infinity upon T naught minus T infinity equals to cos HM LC minus X upon cos HM LC. Okay, now this LC is nothing but it is the characteristic dimension, and this is equals to volume upon area. So the value of LC is equals to volume upon area. This is called as the characteristic dimension. Oh, I am so sorry. This LC is not the characteristic dimension. Characteristic dimension was L. Okay, this LC is actually the corrected length. I'm very sorry. LC is the corrected length of the fin, and LC, that is the corrected length of the fin. In case of rectangle is equals to L plus T by 2, and in case of circular it is LC for circle is equals to L plus D square by 4, where T is the thickness and D is the diameter. Okay, this is for pin type fins, pin fins, and this is for the rectangular fin. Now for the third case, if I wish to write down the Q conduction through the fin, that will be equals to under root PH KA T naught minus T infinity tan HM LC, where LC is the corrected length. Okay, this is the corrected length, this is not the characteristic dimension. So this formula also needs to be remembered. This is also a very important formula. So we have now discussed all the three cases of the fins, their conduction formulas and conduction of heat transfer formulas, along with the temperature distribution profiles in each case also. Now, one very simple and important topic that we will discuss is fin efficiency. What is the efficiency of the fin? It is represented by the symbol eta, and efficiency of the fin is equals to upon, that is Q actual which is taking place upon the Q which is maximum possible. Q maximum possible. So as we know that efficiency will be definitely less than 100%. So Q actual taking place upon Q possible. The Q actual will be the Q fin which is either in any of the three cases, whereas Q maximum possible would be the formula for Q maximum would be how much? Q maximum possible will be through convection only, that is HA Ts minus T infinity, where what is A area equals perimeter into length. Perimeter into length into H Ts minus T infinity would be Q. This will be the maximum heat transfer that can occur. Okay, now I am generally writing the direct formulas because derivation is not important. Efficiency of the fin equals to tan H ml upon ml, and we know that m is equals to under root pH upon Ka, so this becomes tan H ml upon under root pH upon Ka, efficiency. Now we see from here that efficiency is inversely proportional to 1 upon under root H. Efficiency is inversely proportional to 1 upon under root H. This is a very important thing which is to be noted here. That is, efficiency is inversely proportional to the heat transfer coefficient. If the value of H is high, then efficiency is going to be low. That is, value of H is high generally for liquids. Value of H is generally high for in case of liquids, and value of H, if it is low, then efficiency is going to be high. That is, this is for air. So the value of heat transfer coefficient should be low, and for that we must use ambient surrounding as air. Okay, the formula that we have obtained here is, that is, efficiency equals tan H ml upon under root pH upon K, or this efficiency of the fin. This formula was for case 2. This formula was for case 2. Now if we discuss for about case 3, then efficiency equals simply nothing but tan H m LC upon m LC, where LC is the corrected length. Okay, and we will also see from here that efficiency is directly proportional to the under root of K, because this K in the denominator will go up and efficiency is directly proportional to under root K. That is, if where K is the thermal conductivity of the fin material, K is the thermal conductivity of fin material, thermal conductivity of fin material. That is, if the thermal conductivity of the fin material is high, then efficiency is also going to be high. Okay, the next topic that we are going to study is effectiveness of a fin. Effectiveness of a fin. The effectiveness is represented by the symbol epsilon, and it is equals to Q, that is the heat transfer with the fin upon heat transfer without fin. Heat transfer without the fin. Actually, the effectiveness of the fin simply represents that how effective is the use of fin when we are having this heat transfer. So this is the physical meaning of the effectiveness of fin, that is how effective is the fin when the heat transfer is taking place. So I'm simply directly writing the formula, that is epsilon equals to tan h ml whole upon under root HA upon PK. HA upon PK. This is the formula for effectiveness of the fin. Now from this formula we will observe that epsilon is directly proportional to under root K and epsilon is inversely proportional to under root H. So these two factors needs to be remembered because a direct question can be simply asked. Now we see that effectiveness is inversely proportional to the heat transfer coefficient, that is if value of H is more, effectiveness is going to be less. More means in case of water, and that is why we are generally not preferring ambient surrounding as any liquid, and if we are having air, then value of H is low and effectiveness will be large. Now one very important point which is to be noted here is that effectiveness, the minimum effectiveness should be nearly about 200%. If the effectiveness is not nearly 200%, then we do not go for fins. We simply do not go for fins. Okay.